problem here says that if we use a cylindrical rod, let's understand what is the problem. Actually, in the problem, there are some lines on a ruled notebook. Let's say some horizontal lines on a piece of paper, uniformly spaced lines. And we keep a solid cylinder. So this is the top view of that solid cylinder, which is kept on that horizontal sheet at an angle of theta with the ruled lines. This is given to you. Now he's making a statement. He says, if the axis of the rod makes an angle theta with the ruled lines, the lines will appear broken if you observe those lines from near vertical location. So the thing is, if they appear, these are the two things that you need to answer in the problem. That you have to explain the appearance of the ruled lines like this, these broken lines. So wherever you are observing the image of the ruled lines from above the cylinder, you observe them to be broken and at a different angle. You can see in the diagram, they are saying they are broken and they are at an angle of alpha with the horizontal and alpha downwards. So the matter of fact is, in the problem, he has given you the value of theta and the appearing lines, the appearance of lines are at an angle of alpha, and we need to find out the refractive index mu of the solid cylinder. What is the refractive index of the solid cylinder? So as I will solve the problem, obviously the reason for that appearance will be explained, and we will also find out the value of mu in terms of theta and alpha. Now, if you look into the core idea behind the problem, it is based on the fact that if I take a half cylinder, let's say I take this half cylinder, right, and I try to position a object across this half cylinder. Okay, so if you try to position an object, let's say you are observing something from this side, and there is some object across this half cylinder, and there are like two orientations of that object. One is this vertical orientation for this vertical cylinder, and the second is the orientation which is along like this, right? That can be perceived as a transverse orientation. I mean, whatever I am showing here can be perceived upon as something which is like a solid cylinder. Now, I am trying to observe everything. Instead of observing from top, I am trying to show you the lateral view, the cross-sectional view. And if you observe yourself to be somewhere here, and those points which are, beneath the cylinder to be at the end of the cylinder somewhere here, right? This point object I am taking somewhere here. Let's understand that in these two orientations, the magnification across the cylinder will be different. Honestly, in one of the orientations, the radius of curvature, or you can say that the radius of curvature with respect to the transverse object will act out as infinity. And for the second orientation, which is the conventional one, like this, for this orientation, I mean, I'm talking about the object to have a vertical orientation here. So something which is vertical here with respect to this horizontal cylinder, the same logic I'm going to apply for this cylinder for the top view. I'll show you. First, let me derive the two magnifications, and then I will directly utilize. What I'm going to do is, if I'm observing something from top, and I observe a line, forget about the image. Right now, take a line which is having some length, L, DL, whatever it is, L maybe, or a differential segment, because all these things I'm going to derive for small sized objects. So let me take a length DL. what we are going to do here is, we are going to divide this dl into two transverse objects. So if this angle is theta, I'll have some dl cos theta here. So I will treat this separately, and I have a sectional length which is dl sine theta. And now I will try to find out the magnified lengths of the image lengths of these two objects, which is dl cos theta, and the second one, which is dl sine theta, right? So let's see what the magnification comes out to be. If this is your cylinder, right, it has got a refractive index mu, and this distance, let's say, is 2r, and you are observing from this side. So for a object which is kept just below the cylinder, right? So we have to base, if I am observing from top, actually I have to only look upon refraction which happens with respect to this pole, right? And for that single refraction which is going to happen here, our simple equation for refraction for object kept here, I'm not showing the length that I will use afterwards. So I'm just deriving the result, presuming to be a point object kept here. Presuming a point object to be kept here, I'm getting mu2. So 1 upon v minus mu upon u, which is minus 2r, is equal to mu2 minus mu1. So 1 minus mu, and r comes out as negative r. Right, that r term will come out as minus r. So let me find out the v location for this object just below the cylinder. It comes out as 1 upon v, that is equal to mu minus 1 upon r minus term mu upon twice of r. And that becomes, it is 2 mu minus 2 minus mu upon twice of r, which is 1 upon v. So that is mu minus 2 upon twice of r. That basically means that you know the value of v now, which is twice of r upon mu minus 2. For a general cylinder having refractive index between glass rod between 1 and 2, we understand it will form a virtual image. So v is coming out as some negative value. We also understand here that m in this case comes out as, like by the basic formulation of refraction, you know that if this is my second equation, I can write m as mu1 upon mu2 times v upon u. So just see in this problem, what is that value coming out as? So that comes out to be, it is mu1. So that is mu, the mu2 term here is 1. V I have calculated, which is 2r upon mu minus 2, right? And u term is actually minus of twice of r. So m for me comes out as, it is now mu upon 2 minus mu. If I solve this, this comes out as mu upon 2 minus mu. And that is the clear observation. That's why what we are going to say now is, for this transverse object having a length of dl sine theta, I will draw image separately. Its image length will come out as, this image length will come out as the object length dl sine theta here. M I will substitute afterwards. So multiplied by m. And as far as the dl cos theta term is concerned, right, let me say that dl cos theta will remain the same as, that will remain the same term as dl cos theta at this point. That is dl cos theta. I'll give you the reason for that. The same approach for the second object, which is aligned like this. The only difference is for that alignment, I mean, we understand that for the second alignment, the radius of curvature will, in that plane, it will actually be infinity. I mean, all the results being the same. Only thing is in that consideration, so I will just write it here. For dl cos theta considerations, what I am saying, it is mu2 upon v. I'm not substituting any value. I'm just choosing the result minus this, and the RHS term here is like mu2 minus mu1 upon infinity, which is coming out to be 0. So you can observe that mu2 upon v term, that is equal to mu1 upon u, and that basically tells me that m in this case will be equal to 1. So that's why I said that if I have to consider this length dl cos theta, its magnified length will remain the same as dl cos. And now the resultant of this, they have already said that this dl cos theta and this m dl sin theta, if you find out the final orientation, they have said that this orientation makes an angle of alpha, right? With respect to the horizontal line where dl was, your effective dl prime, you can say this is your net dl prime, and that is at an angle of alpha here with respect to the horizontal. Remember, this direction as such was theta, right? And that total angle obviously is 90 here. In fact, here also it is 90. So basically this angle is 90 minus theta plus alpha for the dl prime orientation. I'm right. So you have to just take one equation, like let's say you take cot of this. So let me write the final equation. I'm just taking cot of this term. So that is equal to dl sin theta into m upon my dl cos theta term, right? And that will be equal to cot of this angle, cot of this angle. Correct. This is dl sin theta into m here. Dl cos is here. So I've taken cot of this value upon this, and that becomes tan of theta plus alpha. Tan of theta plus alpha. And now obviously dl terms will cancel. So our interest was to find out the refractive index, and I'm getting mu upon 2 minus mu term to be equal to tan of theta plus alpha divided by tan theta plus alpha whole divided by tan theta whole divided by tan. And I think if you eliminate mu from this equation, once you solve this equation further, you should get your answer of mu in terms of theta and alpha. I mean, calculations apart, conceptually, this is the case. I mean, the point is, this setup is like acting like a cylindrical lens, honestly. And for the cylindrical lens, the two orientations or the two transverse orientations which have been given to you, for those two orientations, in one orientation, the radius of curvature is infinity. And for the second orientation, the L there, the R rather, there, the curve as such is more of a planar surface for that orientation, where radius of curvature is coming out as R. So I've just solved that. Then a bit of geometry, and you will get mu in terms of theta and alpha. So appearance has obviously been explained, and mu has been calculated in terms of theta and alpha. All right. There's a laser beam which propagates through a spherically symmetric medium. Now let's understand that this sphere has got a radius of capital R, and the medium around it is spherically symmetric, and refractive index mu is some linear function of r, so maybe k into r. Mu is given there, k into r. All the parameters are given, and the question is like, if you bombard this laser beam at a distance of r naught from the center, and to begin with, the angle of bombardment here, that is theta. So the question was, what is the minimum distance from the surface where the beam can reach? Right, minimum distance from the surface where the beam can reach. If I want to, find out the equation of curve also, let's say, let me just analyze this spherically symmetric medium through a basic property. Let's say this is the system around which the beam has to move. So maybe when I am at a general location, let's say R, and I think of this beam like a particle which has got a momenta of P, and it is forming an angle of theta with the radial direction, right? So as it will move around this system, the angular momenta of this particle, which is P sine theta, the momentum, into R, that will behave like a constant. And now try to, invoke the wave character. So that P can be further written as h upon lambda, and that h is again a constant. So it's like 1 upon lambda into sine theta into the radial distance from the center, r, that will behave as a constant. And now, knowing the fact that the absolute refractive index there is proportional to 1 upon lambda, this equation further converts into, a constant may change, so it is mu into r into sine theta. This is the absolute refractive index mu as a function of r, that will behave as a constant. And as this problem talks about mu being a linear function of r, this becomes k into r, again a constant. So basically, r square into sine theta, that should indirectly behave as a constant. And this equation should help me finding out the minimum distance also. So when he talks about this curve, this beam rather, reaching a point where distance is minimum, so at that place, if I draw the tangent, right, I understand that with respect to r, this is r min for me, and theta there, r min location, that will be equal to 90 degrees. So indirectly, to begin with, what I was given was r naught. So like r naught, so this 50 root 2, and theta initially that was 30, that term is half, and it will be equal to r min square, and there that sine 90 term, that will be equal to 1. So quite evident that r min here will come out, right? Mu that was given as 1 upon lambda term, so that became kr. R term was already there, and I've taken that sine theta term. So r square sine theta term, that was behaving as a constant. So this is 50 root 2 square into half, that is r min square. So r min comes out as 50 mm. If you can see that, it comes out as 50. So basically he said, what is the minimum distance from the surface? So I think easily you can answer that. That will come out because radius of that sphere was given as 10. So that helps me writing the answer as 40 centimeters. So with respect to the surface, the minimum distance from which it will pass, that will come out as 40 centimeters. So very nicely built up objective problem where you can directly answer the value of minimum distance from the center or from the surface of the sphere. Now, in this problem, he is giving you a transparent rectangular slab. It has got a length of 20 centimeter and the thickness of the slab, that is 40 centimeter, right? D is given, L is given, and it is placed in front of a converging lens. And for the converging lens at a distance of F, they have kept a screen. At a distance of F. Now, if the condition is given to you, and this problem is very similar to optics problem that was given in JEE this year, and this is from our class illustration only. So, he said ki if the refractive index at the bottom, that is mu naught, and it linearly increases to a refractive index of mu naught plus delta mu at the highest point, topmost point. So the question was, if you bombard this beam, exactly what are you going to observe? What kind of light pattern are you going to observe on the screen? That was the question. So, if I look into a wavefront, like if I look into a wavefront which was here in the beginning, right? And I want to observe the wavefront at some time instance when the particle here is like, if I'm observing the particle at the bottommost point only, and the instance when that particle has reached here, if I look into A prime, B, I want to just observe the shape of the wavefront at this juncture, at this time instance. So we understand that the time that it has taken, that is L upon some V naught to travel from here to here. I'm assuming velocity to be V naught for refractive index mu naught. And the same time, the uppermost point B has traveled L by V naught time into the velocity there. So maybe VB you can say, V at that place, VB. And that makes it simple because you multiply. So this comes out as the distance that it has traveled, that comes out as L into refractive index at the bottommost point mu naught. And this is the refractive index like at the highest point. So it is mu naught plus delta mu. So what we are trying to say is the corresponding point B has now reached B prime, and distance from B to B prime, that distance is this. As expected, mu was increasing. So we were expecting that part of the wavefront to travel less. It has traveled L and it will travel a factor of L, fraction of L. Now this makes life easy for me because if I look into that section A prime, B prime, right? Now I can see that my wavefront which was plain here and vertical, its orientation is this now, right? And if I just want to find out the angle at which it has oriented, I'll get my theta from that. So I'm writing it, actually tan theta comes out as that D upon that deficit, right? So L minus the lower guy, so it has traveled L mu naught upon mu naught plus delta mu. So basically that is D by L mu naught plus delta mu, and denominator you will have mu naught plus delta mu minus mu naught. So I got a term delta. That is the tan theta term. And remember, once I get the orientation, basically what was going to happen is, if this was the orientation of the lens and everything would have been fine, and the wavefront would have been incident planarly and normally in the y-z plane, You understand that all these rays would have reached the focal plane also at this point, which is at a distance of f on the screen, this point. So indirectly, what we are doing is we are just rotating our setup. Yeah. So like if this is the orientation, then the signal will travel normal to this. So basically, as you come out of this rectangular slab, your wavefront is now at a different orientation. And this angle here is theta. So it is at an orientation of 90 minus theta. So by the same principle, what is going to happen is it will follow the same orientation, and I'll just explain it somehow like this. These waves signals will finally converge at that point. I mean, you can show it like this. All those will converge and the optical center signal will move straight. So indirectly, they will converge at a point where this angle is 90 minus theta, and that distance above the central point is some z. So actually, you have just tilted the setup. So when he says what will happen to the light pattern, so instead of converging at this point in the initial state, now it will converge here. And that point is at a distance z above the point of previous convergence. And z can be written now. It is f tan 90 minus theta. So f cot theta, and that comes out as f L. I'm just writing cot theta from here. First, second, it is L delta mu, that cot theta term I'm writing, and divided by D into that constant which is mu naught plus delta mu. Remember, this can be further approximately written as it is F L delta mu and then D into kind of mu naught. Because, I mean, if you look into the values, delta mu there was very, very small in comparison to mu naught. So F L delta mu upon D into mu naught, that is the distance where it will finally converge. I mean, if you want, you can draw your rays appropriately. The signal shape will be something like this. This is the pattern which is going to be formed, and that is the point of convergence, right? With respect to the lens, so we will remain in the focal plane, but that point will get rotated, you can say, by that distance r theta or f theta or f alpha. Alpha is 90 minus theta. So that's what you have done. So just because of, you can say by Fermat principle also, you'll get the same result. I mean, whatever orientation I have shown here, if you see such problem, like this is also very similar, just to substantiate the idea. I think this will even be better to explain the point. Just go through the problem and apply the previous concept only. Here also, you are bombarding a beam. You're bombarding a beam on a disc. So this is the sectional view of the disc, right? So if you observe from front, the sectional view is this, and refractive index here, you read the statement. Refractive index of a material can be adjusted by diffusing impurities. Moreover, by adjusting concentration, distribution of diffused impurities, a specimen of any desired gradient. This is interesting. Specimen of any desired gradient of refractive index can be obtained. Now consider a thin disc of uniform thickness D made of a transparent material, refractive index of which is to be made to vary with distance r from its center by suitable diffusion of impurities. Now let's focus on the core concept in the problem. Core somewhat is like this: ki if you are bombarding a parallel beam or a disc, it's like a cylindrical beam on a disc, and you observe that this beam converges at a distance of f. You have to observe the front view. The front view is like this. The beam is going through a sheet of paper having some thickness, and finally those rays are converging at a point. So they are kind of forming a solid angle at that point, right? So in this view, I mean, I can only show this thing that they're all converging at some point here, maybe here, something of this sort. And his concern is very clear that if they remember the thickness that he was discussing in this problem, he has given that thickness. Now, this is D, which is small, and this distance here is F, and the radius of the disk, that is not given, but he wants you to find out mu as a function of R. So by the same principle that I have used previously, what I will do is, if all of them have to reach this point, then my Fermat's principle, this wavefront which was here at t is equal to 0, all the particles of this wavefront will reach this point here. So basically, the time taken by this, time taken by a particle which was here to reach this point, and any general particle, maybe a general particle here. Just see this diagram, just to understand. Someone which was here, it will travel across this distance d, and then it will travel in air, it will reach this point, right? The focus, F. And we are saying any other particle at a radius of r. In this diagram, I'm showing the height, but in 3D, you understand that is the radius r. So whatever reaches here, right, that will also move across the medium, that small thickness d, and then has to converge at the same point, because that focus F is given. It is given that the beam converges there. So now it becomes obvious that the time taken by this green, now this is not a single ray, it is a mere representation of all the guys who are at a distance of r. So this represents a general wave for me, or the normal to a general wavefront. And this is the wavefront for r is equal to 0. So what I'm going to do, I'm going to equate the time. And again, instead of time, I can equate the optical path. The optical path for this guy will be mu as function of r, mu d, and remaining that it has traveled in air, that is root of, so f square plus r square. And as far as this guy is concerned, which has the person who has traveled along r is equal to 0. So mu there, what is that? Mu naught, refractive index at the center. So mu naught into d plus it has traveled in air, and that distance is f. Now just use that approximation here. This equation is simply mu r into d plus, and because f is large, it becomes r, and then it is 1 plus r square by 2f square. Now just observe this. This will come out as mu naught d plus f. It will be f, so I have taken f common instead of r. So let me write f. I think now it's simple. Mu r from this can be approximately written. This term will cancel out. So it is mu naught d term will be taken care of minus r square by twice of f into d. And check that. So it comes out as mu naught minus r square by twice of f, and d term will be there. So we will get this result, right? Now there is extension to this problem also, which is nicely fabricated in terms of the shape of interface. I'll come to it, but before that, let me take up more conventional problem for JEE. So in this problem, let's start. Akshat, you want to say something? Yeah.
Yes, sir. I just had a small doubt. If, can you explain in brief as why is refraction even undergoing there? Because the disk is perpendicular to the wavefront, right?
Mm-hmm. No, refraction,
So,
the thing is, what we call upon as refraction, format, refraction is just a way of contemplating the idea that
mhm,
basically these signals have to follow a path across which they take the least time. So while
right,
they go across a medium change, they just want to adopt a path randomly through which, out of all the possibilities, the time taken is minimum. And while they do so, people say that bending has happened. The
hmm,
same thing which Fermat explains like this, Huygens explains the same thing in terms of a wavefront. He says that because these guys who are traveling at different speeds, they
good,
have to, he used a hypothetical idea called upon as wavefront. So he says
right,
wavefront is a locus of all those particles which are in the same phase. So
hmm,
phase for me is actually time, the time for which they have traveled. So that's what we have done in this problem also. So first thing is what has happened. He has observed that all these people, like it is not possible. Even this, in this case, the diagram that I have shown, I'm assuming this thing that D is very, very small. Because within the setup also, I know that as you will move, this guy has to travel, longer distances. And obviously speed is same here. So definitely he would have reached here previously, no? In comparison to this person, he cannot, this person should reach here previously if they have to reach here simultaneously for the image to be formed here. So that's what the thing is. It's more of like when the green one was here, our particle here was somewhat like this,
okay,
right? And while it is traveling in air, now from this point, like when it spreads in all the directions, so for the image to be formed here, if we consider a normal to the wavefront which is moving like this, we are just contemplating that the time which has been taken like to come from here to here is same as the time which it will take if you are saying that the beam is converging at that point.
okay,
So
right,
this is how the phenomena happens, and you can understand this is only for 2 points. Now I have to consider all the points appropriately. So that's what we are trying to say, that we are trying to write a general expression for R on the basis of the mu, because mu we are manufacturing now at different R values. We are just ensuring that everyone who crosses this medium, now for the possibility of a wave traveling from the exiting point to the point where focus is, the time should remain the same. If it happens, then all of them will converge. So we hypothetically manufactured the problem for that beam to converge at that place. In this case, again, there is a capillary tube which has got a outer radius R0, and it is made up of glass of refractive index mu. It is filled with liquid, right? Having refractive index mu1, and mu1 is less than mu. The question is somewhat like this, that you have to find out the minimum internal radius of the capillary so that all the light incident on the capillary enter the liquid. All the light incident on capillary enters the liquid. So I will try to, show this data like this. Let's say the outer radius R0 is fixed, right? The inner circle, this radius is variable. Like, try to understand this. R inner is a variable. So I can change this. And inside you have filled up liquid. That refractive index, this refractive index of liquid which is inside the capillary tube, that is mu1, right? And given that mu1 is less than mu, remember, this setup has got a refractive index. This has got a refractive index which is mu, right? Now you have to just explain it like this, that all the light which is coming from outside should enter, he has given that, should enter the liquid. Now we need to, write equation appropriately. And obviously, you understand that I will put a condition on R. I'll try to find out the limiting radius in this case. This is a nice objective combination. Try to use the previous principle which I have given you, which I have explained in terms of angular momentum to answer this problem. Just see, are you getting your results appropriately? So that ray for which we can, justify. I mean, I am taking a ray diagram. You just think why this satisfies all the possibilities. If I take a ray which is coming along the tangent, so I'm trying to draw the limiting combination. I'll explain it. And it deviates, right? So this angle here is 90. Let's say this becomes some angle alpha. So basically that is critical for me. So I just wrote that equation, which is sine of alpha is equal to, now here it is mu, bahar wala hai 1, so 1 upon mu. So I said out of all the rays which can hit the surface, this is the limiting one, where the angle with respect to the normal is highest. So all the remaining rays will be below this. So we understand that, right? Now, if this ray hits the surface, now again it is moving from denser to rarer. And if I just say that whatever angle it hits at, it becomes tangential. I mean, or you can say, like, if this angle is beta, here it becomes tangential to the surface. Now, if this happens, that is the second equation, which is mu1 into what? Mu1 into sine 90, that term becomes equal to mu into sine beta. Just observe this, and then I will also explain that why this is the combination that I am considering. And now easily you can see that this was the normal, where the radii have been given. So this is Ri, and this distance is R0 for me. And this angle here is pi minus beta. Apply sine rule in that triangle. So that becomes sine beta upon R0 is equal to sine alpha upon Ri. Sine alpha upon R. So what happens is I have to find out the internal radius. So Ri for me from these three equations is coming out as R0 into sine alpha upon sine beta. And just see that sine alpha term comes out as 1 by mu, and that sine beta term is mu1 upon mu. So more appropriately, this comes out as R0 upon mu. And now I want to have that observation. Now we need to theoretically check this. He is saying that this is the minimum radius. So that means indirectly what we are trying to say is, if you decrease your radius further, this is the minimum for all the light to enter. Remember one thing, if in this limiting combination, I change my entry angles here, you understand that if this is just able to enter, then for anybody who is coming like this, any other angle, which is actually hitting it somewhere here, right? This will obviously enter because the angle here is further less, so it will obviously enter. So if the tangential one is entering here, all the other rays will also enter in this combination. So that is about this tangential combination. And now the second point comes that why I am treating this to be the minimum internal radius. If you further reduce the radius, there will be rays which are not going to enter. That is quite obvious now. Because if I change my radius now, the impact point will change further on the basis of change of radius. And that will be at an angle which is greater than this combination beta. Beta is acting like a critical angle. So obviously, it will not enter. So the reason we are calling minimum radius, you understand that. First of all, I have taken one radius for which I have taken tangential incidence and a critical here. This covers up all the incidences. And then I say, even for that green incidence, if I reduce it further, I will find some rays which will not enter, because you can see that angle which I am showing there will be greater than beta. Even the previous concept which we have derived in terms of angular momentum, that thing also somebody can use. So just to give you a glimpse of that idea, there we are talking about 1 by lambda. So we are talking about a mu I, right? Then I have taken that sine theta I term, and then I have taken a Ri term, right? So if I just substitute all those values, right, I have to find out that R inner. So now you can check this term there. The same equation holds exactly. I mean, analyzing it this way or the previous mechanism, R term into mu. So R inner into mu1, the refractive index. And that is R naught into 1. Sin 90 is also there and 1. So this all is actually summarized here also. So by this method also you're getting the same result. You understand that in these problems I am taking only 2 refraction. As you change the number of mediums, right? I mean, writing equations at every location will be tedious task. So this concept will definitely help you out in solving such problems. Okay. Let me take up one subjective problem where I want to derive. Just observe this question. Now, in this problem, you have to derive the equation of the shape of a glass rod. If I just read the problem. Problem is, what is the shape of the, and there are 2 combinations actually. I'll derive one of them first. What is the shape of the blunt end of a glass rod that would focus at a single point within the rod all the light rays which are incident upon it that are parallel to the rod's axis? Very interesting. There are a few questions I will put up. Just listen the questions. पहली चीज तो ये बोल रहा है कि यार, if you bombard a beam on a glass rod, it's not possible that all the rays hit a point. But if you want all those rays to finally hit or reach a point on the axis of the glass rod, the surface of the glass rod should have a unique shape, right? So it should have a unique shape. What is the equation of that surface, shape of the surface? And you have to express the equation in terms of the refractive index of glass, the focal length f, which is defined to be the distance within this. So this is the A part of the problem. I'll discuss B further If you understand A, you can obviously derive the result for part B. So let me explain what is happening. The question is somewhat like this. This is the shape. Let's say this is the glass rod, and maybe here I have got the origin, right? Now this becomes my y-axis. This is the x1. What is happening for the rays? All the rays which are incident are finally hitting a point F. And this can be a very nice objective problem. We are solving in a subjective way because we need to derive that result. Actually, all of us understand that this cannot be spherical, or neither it is parabolic. Let's be very clear about it. It's not a paraboloid. In 3D, this shape is not a spherical shape, neither it is paraboloid. If you want your beam to converge here, this is a different shape. That's what I need to derive first. What is the shape? So x-axis, y-axis. Quickly, I will write some equations here. Maybe this coordinate. So I'll take a general point, xy on the curve. I'll derive the equation for xy. Again, up to this point, wavefront, same phase, nothing happening. Now you are entering this medium, so refractive. So simply write NF, that is optical path length. Here you have got x, and quickly you can write this distance is n into root of what this will become. This is x, y. So this distance is f minus x. Now simply solve it. It is f minus x the whole square plus y square. Actually, this is the equation of x versus y. This equation will give the shape of that blunt end for all the rays to reach that point, which you are calling as focus. If you derive it, I think it becomes an ellipsoid. So I'll just derive. So NF minus x the whole square, that is n square, and f square plus x square minus 2fx plus y square, right? So basically, x square minus 2nfx is equal to n square x square minus 2fx n square plus n square y square. Now check that it comes out to be an ellipse, because it becomes n square minus 1, 0 is equal to n square minus 1 x square, then minus 2fn x into n plus 1. No, minus 2fx n square and then plus. So this term will be minus here, minus 2fnx, that's perfect, and plus n square y square. That's what we are getting. Now try to just convert this. Right, it is x square minus 2fn x upon n plus 1 and n square y square upon n square minus 1. And now I'll write the equation. Now this is the final step. So x minus nf upon n plus 1 the whole square plus n square y square upon n square minus 1 is equal to RHS. I will have nf upon n plus 1 the whole square, and now divide by this term. This becomes 1. Now it is x minus nf upon n plus 1 the whole square upon nf upon n plus 1 the whole square plus, just try to write this carefully, y square, upon. So what are we getting? And is n square minus 1 into f square upon n plus 1 the whole square. Basically, what I'm trying to say is there are two interesting points I want to make. First thing is that curve is ellipsoid. This equation here talks about in 2D is saying that it is ellipse. So basically, I'm making that statement. It is ellipsoid. Then the second thing which comes up is this point the focus of that ellipse? So if you just look into the shape of this curve, right? I mean, actually, this is the right-hand side ellipse. Just draw everything here and you will perceive this. The curve is somewhat like this, right? This is the blunt face, and then I've got a center, then I've got these two foci, F1, F2, and basically I'm getting my beam like this, and here somewhere is my origin, and my x-axis and y-axis. I definitely wanted to find out that will this beam, okay, this equation is ellipse, does it hit the focus? I mean, in ray optics, this is focus, but actually the ellipse which has been formed, are the beams getting converged on the actual focus of the ellipse that we have drawn? Why I'm so specific about this is because when we solve the counter of this problem, there is no such concept that they will reach the focus only. There we will justify that the beam will not reach the focus of the conic section which will be formed. In this problem also, you have to be very careful. That's why I was saying you have to be careful. I mean, look into this. Your center is at nf upon n plus. I'll spend some time, don't worry. Nf upon n plus 1, 0. This is your center, right? And A is also nf upon n plus 1, so that's fine. That's why I've drawn this distance also, right? And further, you can now check that B distance is, what is your B? It is f root of, this is n plus n minus 1 upon n plus 1. This is f root n minus 1 upon n plus 1. So this is f root n minus 1 upon n plus 1. Now do one thing, that is one assignment we will all do. I have drawn the ellipse properly. I've shown the two axis length. Now, you know, you have to check this distance, is it equal to f? Are the beams coming here? Or you have to check this distance, is it equal to f? Or f is somewhere else, neither the focal point, none of the focal points of the ellipsoid, it is somewhere else. This is what you have to check. And very simply, you can now find out the distance from this corner to both the focal points. Check, I mean, just to accomplish this, check what is OF1 equal to. Just let us write that. So it comes out as A into 1 plus, that AE distance will be there, no? So A into 1 plus E, and that A is what? NF upon N plus 1 into 1 plus E. And now this is equal to E into A, and A is how much? NF upon N plus 1. So I think now everything is fine. You substitute the value of E there, and you should get the result. It is root of n minus 1 upon n plus 1 and n plus 1 upon n. Check, is this value coming out as f? Then you check OF. I think all of you got the idea. What I am trying to talk about is, once I get a particular curve, directly stating that it will hit the focal length is not a wise proposition. There's no reason to directly state that until unless I have proved it. So basically, this question is talking about the same. Here we can derive that result and check. All right, you can accomplish this problem. Second part also, I'll try to take up in next class, where I will counter that point. So just solve it. I mean, I've written everything here, and you will verify the facts which I was trying to share with you. Okay, fine. So I will finish off this class here, and we'll catch up again next time. So go through these small ideas, which will be they will be helpful for you in your advanced examination. And I'll see you next time.